Well, welcome back, guys, and I do hope as ever you and your family are keeping well, even though sadly you can't be here because of all this problem with the virus at the moment. So what we're going to look at today is the second lesson on magnetism, and we're going to look at electromagnets. What electromagnets are, how we can make them stronger, and what we use electromagnets for. So for our first bit of work on electromagnetism, I'll clear a little bit of space here. And what we're going to do is see how we can make an electromagnet. So we're going to start off very simple, and then we're going to get a little bit more complicated. So I've got a piece of apparatus here that is literally just a piece of card on a stand. And what's important is I've got a wire running vertically through a hole in that piece of card. And what we're going to do is we're going to pass some electricity through this wire. So over here, it's a bit out of shot, is a power supply. And I'm going to turn the power supply on and pass current through this wire. Okay, so we've got one piece of wire and we've got a source of amps, current from the power supply. And I'm going to connect it so that down here, the bottom is connected to the positive terminal and the top is connected to the negative terminal. So the current will run upwards. It's important we know which way the current is running. Now, just before I move the camera and show you what goes on here, I need to just mention a couple of things. Firstly, forget the complexity of the apparatus. It's a single wire with current moving vertically through it. That's the first thing. Secondly, it's copper wire covered in plastic, and copper wire is not magnetic. Okay, copper is not a ferromagnetic material. Thirdly, and I'd like you to think about this in a slightly odd way, this is like a loop of wire. It comes out of my power supply, up to the top of the stand, down and back into the power supply. It's one turn, okay? And we're going to use that term turns a lot when we talk about electromagnets. So this one has got one loop, one turn of wire. And without spoiling the story for later on, what would happen if I brought the wire up, down, back again, etc., and had more turns? Well, we'll look at that in a minute. But I'm going to move the camera now, and I'm going to show you what happens when we pass current through a conductor, the magnetic field that it creates. Okay, now let's look at the magnetic field due to that long straight wire. Okay, so the easy way to do this is to turn the current on, and I'll turn it up a bit, and then to sprinkle some iron filings around this. Okay, now the pattern you get, I'll just do that, turn the current up a bit, is really not very clear, but it's beginning to show. There we go. Okay, I have to tap it a bit to let the iron filings move. So we've got current in our system coming upwards, and you can just about see the iron filing shapes. They're rings around the wire. Okay, they form a magnetic field that goes in circles around the wire. Now you'll notice the iron filings out here haven't done very much. So the magnetic field gets weaker and weaker as you go out, and the field lines, which are circles around the wire, are closely compacted close to the wire. That's where the magnetic field is strongest. Now, remember, we can use plotting compasses to show the shape of the magnetic field. So what the plotting compasses are doing at the moment is pointing sort of this way, which is towards the north in my laboratory. That one is pointing a little bit towards the iron in the stand, as you might expect. But let's turn the current on and look what happens. They all swivel round. I'll turn it off and they go back to pointing along the Earth's magnetic field. So look again at the shape that the plotting compasses form when I turn the current on. That way, that way, that way, that way. In other words, circles or rings around the wire. Okay? And one of the things you need to know is which way those circles go. So we'll look at that next. So you need to know for GCSE which way round the magnetic field goes around a straight conductor like this one. So I'll just turn it on again. And you'll notice the compasses are going around anti-clockwise, okay? You can't see the power supply very easily from here, but the positive is below and the negative is connected above, so the current is coming upwards. So there are two ways to do this. I'll show you the one that's in the GCSE textbook. You take your right hand, okay, you're going to get so confused with which hand you use with all these magnetism things. Right hand grip rule. So take your thumb and point it in the direction that current's moving. So in this case, it's moving from underneath to above. It's moving upwards from plus to minus. And grip the wire with your right hand with the thumb pointing upwards. And you see that my fingers curl around anti-clockwise in the direction of the magnetic field. But what I'm going to do now is turn off. Okay, compass is realigned with north in my lab. Swap the wires on the power supply. So now the negative is up here and the positive underneath. So current is going downwards. And I think you know what happens. Turn it on and you'll notice the compass is going around clockwise, but you have to use your right hand with the thumb now pointing in the direction of current, right hand grip rule. And if I grip it with the thumb pointing from plus to minus, the way the current's going, you'll notice my fingers curl around clockwise. So that's one good way to draw on a diagram which way the field lines are going. Now, there's another way to do this, and I really like this one. I find it an easier way to work out which way the circular field lines go round. Okay, I use something called a corkscrew rule. And if you maybe you haven't used a corkscrew, why would you? Okay, but if you think about the way I've got it set up now, okay, I've got the positive at the top and the negative at the bottom, so the current is moving down. And think about a jar lid or a screwdriver. If you want to put that lid on, in other words, move it down onto the jar, you're going to turn it clockwise. And there we go. There's the field going clockwise. I'll just turn off. Okay. I've swapped the terminals on the power supply. So now the bottom one is positive and it's coming up through the piece of paper to here, which is negative. So the current is coming upwards. Think about my corkscrew rule, okay? If you used a corkscrew and you turned it to move it upwards, you would turn it anti-clockwise. If you had a jar of jam or something here and you needed to move the lid upwards, you would unscrew anti-clockwise. Let's just check. Grip rule, current moving upwards, yep, anti-clockwise. So if I turn on, there we go, the field line's going around that way in an anti-clockwise way. So I think about a screw being moved upwards, being undone, and as it comes upwards, I would have to turn it anti-clockwise. So we can draw the field lines and we can gain an extra mark by drawing an arrow for the direction of the field lines. And the bit I didn't mention is, you need to know that because it's not clear with wires and circular magnetic fields where the poles are. It doesn't work quite like that. There isn't a north and a south to go to. There's a circle that you have to draw an arrow on to show the direction of the field line. Now, this is getting quite warm as well because of the current flowing through it. So I'm going to turn it off and my compasses are all going to swing back to pointing to the North Pole of the Earth. So I hope you now understand that a conductor carrying a current creates or has a magnetic field around it. But we talked about how to make that magnetic field a bit stronger by turning up the current. But of course, the other thing we mentioned was what happens if we have more wire coming up here. Now, it's really important they're separate turns, separate loops. In other words, they're not touching, because if they were touching, they'd kind of merge into the same wire. So they have to be insulated turns of wire, and each one is going to have a magnetic field. So if we have lots of turns, all those magnetic fields are going to add together to make a stronger magnetic field. So let's look now at what happens when we make lots and lots of turns. We have a specific coil of wire that we're going to call a solenoid. So you've seen the magnetic field due to a single wire, and we said to make it stronger, why don't we have more wire in the form of one wire next to another wire next to another wire? In other words, lots of turns, and each one will become magnetic. Each one has a magnetic field associated with it, and those magnetic fields will add together to make a stronger magnet. Now, if we wind it, I can't do this very easily on my hand, but if we wind it where the turns are all next to each other with gaps in between, you can still put them very close, like this thing. You end up with a coil, not lots of coils, a coil of wire with lots of turns on it, and they're all sitting next to each other. So they make a shape that is pipe-like. And if we convert that to Greek, solenoid. So a stronger electromagnet is going to be a solenoid. Lots of turns of wire wound next to each other with current passing through them. Okay, I've got a solenoid here. I hope you can see that it's one wire with lots of turns. They're not very close together. They're separated, so they each behave like individual little magnetic fields. And I've put inside some plotting compasses so you can see the shape of the magnetic field. And at the moment, they're all pointing sort of that way. That's the north in my laboratory. But let's turn on the current now and see what happens. So on goes the current, and you'll see them all swivel round. I'll turn it off, and the magnetic field disappears. So if you look carefully, you'll notice the plotting compasses show the shape of the magnetic field due to the solenoid. Have a look here. The north points that way, that way, that way. Then it comes round and points this way towards me. Then it goes along, in towards this end and back in. Okay, so you've got rings of magnetic field going around like that. So if that's the north of a compass, it's pointing to this end, which must be a south pole. There's the south of the compass pointing to this end, so that attracting must be a north pole. So we're coming out of the north, around and back in. And the same is true on this side. We come out of the solenoid, around and back in. Okay. Did you notice something there? That the magnetic field shape due to a solenoid is exactly the same as a bar magnet. Imagine that that's a bar magnet. You've got magnetic field coming out of the ends, curling round and coming back into the other end. So a solenoid is a kind of electromagnetic bar magnet. And I'll just turn it off. As soon as you turn it off, of course, it has the advantage that it loses its magnetism. So let's quickly make an electromagnet. So I've got my power supply here, and we're going to have lots of turns of wire. And to be honest with you, it takes a while to make these, but if I get my single coil, stuck on my fingers, there we go. Okay, and I connect it to the power supply. It usually all kind of falls apart in your hand, but let's get that connected to the positive. And my other end, I don't know how many turns I've got on here. I should have counted them, I suppose, but there we go. Connect that into the negative. And this will make an electromagnet. I'll grab a compass. Okay, and that compass doesn't move at all when the copper wire is there. But let's turn it on. So we're on, and I think you can see I hope you can see the compass needle swinging round. It's probably not very clear on the video, so I'll move to there. So magnets on, magnets off, magnets on, and the magnets off. It's not a very strong electromagnet. We've got two good things here. We've got loads of turns, that makes for a strong electromagnet, and we've got lots of current, lots of amps, so it's getting quite warm. But what would happen if we took a soft iron material? So that's a material that can be magnetized, but when you take it away from a magnet, it loses its magnetism. So it's an induced magnet. And if we put that in the middle, the magnetic field from the turns of wire will make this piece of metal magnetic as well, and that makes for a much, much stronger electromagnet. I'm not sure if this one is strong enough to It's not strong enough to lift up a bit of iron, but we'll see in a second whether it'll lift up a few paper clips. So I've got some paper clips here, and we've got our electromagnet. I'll turn up the current, and well, we saw it move a compass needle, but it's a very weak magnetic field. So remember, let's make it stronger with a core, a soft iron core. And now, yeah, it's not meant to be very exciting, but it does pick up just a few paper clips. So we're going to take that a bit further and see if we can make a much stronger electromagnet now. So for a really strong electromagnet, we need our source of current. So that's our power supply. So I'll just plug in there. We need a coil of wire, and this is lots and lots and lots of turns. It says on here 400 turns on this coil of wire. So power supply is off. I'll plug into the 400 turns. We'll turn up some current, so we're on, and here's some current. And yeah, it's pretty good at picking up paper clips, and it's an electromagnet. But to make it stronger, remember, we need a soft iron core. So we'll put the iron core in the middle and turn it on. And yep, that's pretty good now. It's a really strong electromagnet. Just turn it off. Okay, a little bit of residual magnetism there, but basically the soft iron core was induced magnetism and has lost its magnetic field. But the one I love doing with pupils when they're in class is I'll take a laminated iron core. So this is some iron that's in flat pieces, and they're stuck together with insulation in between. So it's kind of stripy. Okay, and I'll put that piece of iron inside the electromagnet, turn it on, and yep, no problem there. It picks up the paper clips really well. And finally, do you remember we couldn't pick up or move this piece of iron with our weak electromagnet? So let's turn it on now. Okay, and that, I'll be honest with you, I will not be able to get this apart whilst it's on. Okay, that is a very strong electromagnet. I'll just turn it off. There we go. Soft iron core. What I sometimes do is I put the very strong electromagnet like that on the paper clips and then turn upside down. And, well, some of them are hanging off, not all, but the magnetic field can pass through the plastic of the paper clips box. Oh, I was a bit annoyed with myself there, spilling all the paper clips and then having to clear them up. But, of course, the answer to this is obvious. Electromagnet. So there we go. That's some of them. Turn on again. Oh, let's take that. Oh, it's not going to stick to that one. Might do that way. There we go. And we can put it all back here. All packed away. So there are lots of uses of electromagnets, and this is a really nice device that uses an electromagnet, and it's called a relay. And this is something that you need to know about. The trouble with relays is there's so many different ways of putting them together and drawing them in textbooks. But what I'll do is I'll try and explain this little model that we've got in our laboratory. So let's demystify it. Firstly, do you see turns of wire here? Okay, those are a couple of coils, a couple of solenoids on a soft iron core, and I've got it connected to a battery which I haven't yet switched on. Well, you know what happens. If I switch this on, the current in these, this will become a strong electromagnet, and here's an iron bar, and what it will do is it will pull the iron bar closer to the magnet. Okay, so we'll just do that, and you might hear it. There we go. So all you're looking at here is this little circuit turning on an electromagnet and pulling a soft iron bar, armature sometimes we call it, okay, towards the magnet. And it's on a sort of spring system, so as soon as I disconnect the current, it flicks back to where it was. Okay. Now, separate circuit. Between here and here, I've got two separate contacts. It's very difficult to see them, but it's two contacts that are separated, and they're going to push together and disconnect. So when this bar rotates, look here, it pushes these two contacts together. So let's have a completely separate circuit. Okay, so I'm going to connect to the bottom connector here, and I'm going to connect to the top one. And currently in the gap there is a bit of air. But if we push those two contacts together, it switches on this circuit. Now, instead of doing it with my hands, why don't I do it electronically? Why don't I do it electromagnetically? So here we go. Switches on, and as soon as I switch off here, which could be about 8 miles away, if we've got the right cables, I can disconnect. The history of these, I could go on and on about. They're used for lots and lots of things. They were used a lot on the railways in the early days to send signals like Morse code. I used to play with pinball machines when I was a kid, and these were the things that made the bumpers and the scoreboards all score. Old-fashioned dial telephones, some of you have seen the one in my lab. When you turned it, it went chick, 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 and in fact relays were used to route the calls. But what do you need to know about relays? Okay, its use is for GCSE, where you can use a very small current, or maybe a very low voltage, to create a magnetic field. But that can attract a metal bar and turn on a circuit on this side, which could be very high current, turning on large motors in a factory, or it could be turning on a very high voltage. This could be like mains electricity that we never want to touch. The example I always give is a 6-volt battery with a relay turning on swimming pool lights. Okay, and if I touch any of this side, I'm never going to get a shock, but if I was to touch this side, I would. Can you see why it's called a relay? It takes the on-off signal from this side, switches a switch on and off, and turns on something else. It relays the information. So I hope you can see here two completely different circuits. Okay, an electromagnet turning on a second circuit. Now, what I'm going to do next is just very quickly whiz through what you would have to do if you had to explain the relay and how it works. So, if in an exam you have to explain how a relay works, it's best to break it down into a series of bullet points where one thing leads to the next, leads to the next. Okay, so I turn on a power supply here and a current flows in the wires and in these turns. That creates a magnetic field in the electromagnet, which attracts a soft iron, an induced magnet bar. That bar then pushes two contacts together, which then makes or switches on a second circuit, which is typically higher current or higher voltage. Okay, so can you see how I went through each step there? Okay, leading to how this light bulb would light up. So that's an electromagnetic device. It's the relay. Again, I could say so many things about this. If I could get a system that turned on and off and on and off and on and off, which is possible, and I put a bell here, that would be the pring, the ringing doorbell. Okay, that's quite a clever system whereby the electromagnet pulls a circuit together, and as soon as the hammer hits the bell, it disconnects the circuit and it resets and then rings again. All I can do with this one is sort of make clicking noises. But that's the relay in use. And I bet you couldn't have understood that unless you understood something about electromagnets. So I just wanted to quickly point out something about the relay demonstration that I've done. Because this relay system little demo was made here at school, and I'm really grateful to whoever made it. However, from a teaching point of view, it's much better to think of relays as having the switch that you press to get it to work on the left, and the output of the system that switches on the high current, high voltage side on the right. So let's flip the picture around now. And if you look at the picture flipped the other way, that's a more typical way of drawing it, especially in an exam situation. In other words, the little switch that switches the relay on and off is on the left, the input is on the left, and the high power circuit is on the right. So in many ways, the way it's on the screen now is the best way to think of the relay, as being switched on the left, input on the left, and switching some device on, output on the right. Great, so we'll go up to the board now and I'll jot down a few little notes on everything we've done today, so you've got a written example of the work I've been trying to teach you. So let's summarise what we did today with electromagnetism. So electromagnetism. Right, so the first thing that we really looked at was the magnetic field due to a wire. Okay, so the magnetic field due to a straight wire. Okay, so if you remember, what I did for that was I took a piece of card with a hole in it and I passed a wire through it. So here's the wire going through the card. Just get that a bit straighter, and coming out underneath, and then that's connected to a power supply top and bottom. Okay, what we noticed was that the magnetic field formed rings around that wire. So when we turned it on, we got a magnetic field pattern that was circles around that wire. And I'm going to draw that a little bit bigger in a minute, and I'm going to put the direction of those circles on. Okay. We noticed two things that were really important. Okay, that the magnetic strength, this is something new, the magnetic flux density. Okay, we're going to give that the letter B. That's all we need to know for GCSE. B. It's sort of the strength of the magnetism, the magnetic flux density. I'll explain that very quickly. How many field lines you've got, how many magnetic field lines you've got in a certain area. Okay, that depended upon current. Okay, so the magnetic flux density went up as the current went up. The magnetism got stronger as we increased the current. But also, when we backed away from the wire, the magnetic flux density, the strength of the magnetism, gets weaker and weaker and weaker and weaker. You don't need to know exactly how it falls away, but the magnetic flux density gets smaller as the distance R from the wire gets bigger. Okay, don't worry about the details of that. It's just the fact that as you get further away from the wire, the magnetism gets weaker. So in other words, the field lines going around the wire will spread out and then be further spread out and then much further spread out. So they're concentric circles, but they don't all separate by a centimetre, then another centimetre. The gaps between them get wider and wider. So now let's look at what happens to the shape of that field, because we need to draw a direction on. Okay, so the way I do this is I look at it from above, okay, and I draw the wire coming straight at you. So here's the wire with you guys looking above, so sort of looking down the wire. Now, if you think about this, if I make the bottom positive and the top negative, current will go upwards. Okay, so what you have to think about is a dart going upwards, current going upwards. Do you remember a thumb on the right hand grip rule? In other words, a dart coming towards you, so you see the point of the dart. So there it is. Okay, as soon as you see that as a physicist, you think, oh yeah, I get it, that's the cross section of a wire viewed end on with current coming towards you. So the magnetic field lines around this will be circles, and the next one is much further out. So they're close and then they spread out and they spread out even more. Now you need to draw a direction. So how are you going to do this? Corkscrew rule. If you want something to come towards you, you have to turn the lid or the corkscrew that way to get it to come up. right hand grip rule, you grab hold of the wire with your thumb pointing in the direction of the current and you're curling round anti-clockwise. So that completes that diagram. But now let's turn the power supply around and connect the top to positive and the bottom to negative. So the current goes downwards. Okay, so I'm going to redraw the wire over here. Imagine a dart, okay, you're looking from above always, going downwards. What you would see is the back of the dart, yeah, the flights or the fletchings of the dart. In other words, across. And every physicist would recognize that as looking at the cross section of a wire with the current going away from you. These diagrams are really important for what we do later on with motors. So we know the magnetic field is going to be the same shape, rings. We know that the spacings are going to be identical to this diagram if the current is the same, just the opposite direction. And then, I know you know which way to put the arrows on, but let's just look at it, okay? Corkscrew rule, or putting the lid on a jar, okay? You turn it that way to get it to go away from you, to screw a screw into the page. Right hand grip rule, okay? The thumb is the direction of the current and you grip it like that. So your fingers are curling around clockwise. So the arrows of the magnetic field direction are pointing that way. Okay, so you now can complete a diagram of the field due to a long straight wire, and you can put the arrows on it. So important when we do motors. I'm going to say one thing that I hope you understand. Okay, it's really clever when we do motors. These two diagrams could be one piece of wire at the same time. Okay, think about it. If we had a single turn of wire, okay, what would happen if we connected it up so the wire went into my board, round the back where you can't see it, and then back out again? You get a wire going in, behind and out, a single turn, and of course that then would be the combined magnetic field that you'd see. And these combined with another magnetic field are going to be really useful if we want to make a motor which takes electrical energy and turns it into kinetic energy. So the next thing we looked at was the solenoid. And if you remember, solenoid we described as being pipe-like. So it kind of had this shape. You could put the coils, more correctly the turns, it's only one coil. You can put them closer together if you want, okay? And you remember, to make it an electromagnet, we attached it to a power supply. There we go. And we had a current flowing in it. So there's the current I. And we noticed that with the plotting compasses, that it had a magnetic field associated with it. And that magnetic field was quite weak because the current was low, because there weren't many turns, and we didn't have a soft iron core. But what we found was it had poles at either end, and its magnetic field was very similar to that of a bar magnet. So to make it stronger, we turned up the current, we had more turns on our solenoid, and we put a soft iron core in, okay? And if we put the soft iron core in, it sort of sits inside like this, okay? Now, I'm not going to show you how to work out which is the north and south pole. I don't think you need that for GCSE. But shall we just draw it as having a north pole here and a south pole there? Okay. And if you remember, it had a field shape just like a bar magnet. Okay. Out of the north and into the south. Exactly like we've done in the previous video. Okay. So look at the features you need there to make a strong electromagnet. Lots of current, lots of turns. Yep. The textbook says put the turns close together. I'm not so worried about that one, to be honest with you. But put a soft iron core inside and you'll make a strong electromagnet. Now, I couldn't resist doing this one with you actually, to actually show you where the poles are. It just seems too good an opportunity to miss. So if you look at the way I've drawn this one, there are loads of ways to work this out. But the kind of proof that it's a bar magnet is, if you look at the current going this way, there's my thumb, right hand grip rule, you'll see that my fingers curl around this way. So come out of this end, okay, so that must be a north, and the field lines will go round to the south. Now what's interesting is that the magnetic field will go around this one, and around the next turn, and around the next turn, and the next, and can you see that has the effect of them adding up, and all sort of pointing that way through the iron, okay? So the magnetic field will come out, around and back in, out, around and back in. So it makes this end north, it makes that end south, and there is the direction of our field lines. Clearly there are going to be more field lines and those going out a long way that I can't fit on the page. But it's actually quite a nice application of the right hand grip rule to work out which are the poles. So I don't think you'd ever get that at GCSE. So for the sake of completeness and a diagram, because I know some of you will want it, here's a little sketch of the right hand grip rule. We've got current going upwards, okay, so we use our thumb pointing upwards and we curl our hands around the wire. So this wire will have a circular magnetic field going around it, and that circular magnetic field will go round anti-clockwise, yeah, in the direction that the fingers curl around the wire. So finally, let's have a look at the relay. Now you can draw this in hundreds of different ways, so you need the ability to generalize, in other words, to look at a diagram and go, okay, I can see what's going on there. So if you remember, a relay consists of two parts. A circuit that is an electromagnet. So that's pretty quick to draw. So here is our soft iron core. So it can be an induced magnet and then lose and gain its magnetism as we turn off and turn on. We're going to have some turns of wire around it. Okay. We're going to have a power supply. And there is our switch to turn that electromagnet on and off. Okay. The next thing, if you remember, is we had a magnetic material that would tilt, that would be attracted to this when it was turned on and off. And I'll draw it like this. So I'm going to draw a piece of soft iron pivoted about that point. Okay. Now, I'll come back to how it resets, but when you turn on the electromagnet, this pole attracts that piece of iron and causes it to swivel downwards. And if you attach this end to a little spring, okay, I think you can see that when you switch off, this magnetism disappears, the magnetic field collapses to zero, and that will flick back. Okay. Now remember that because this is an induced magnet, never mind which way round you connect this power supply, it will always be attracted to a pole, whether it's the north or the south. Okay. The next bit, and I'll switch colour for this, is we need this to tilt up and to push two contacts together. So the way I usually draw this is I draw a contact here and I draw another one above it, and I tend to draw the one above it thicker just for the sake of explanation. Okay, so engineers would call this normally open, and then when we turn on the electromagnet, this flicks up, pushes those two contacts together because the bottom one is flexible. Okay, and then all we need is our external circuit, and you can make your external circuit anything you like. For example, shall we connect to the mains electricity? So that's a very high voltage, 230 odd volts at 50 hertz AC, that we don't want to get our fingers into. Okay, and then we can connect maybe some mains lamps. Now I've chosen to do a really old-fashioned symbol for a lamp there, okay, like a filament lamp. I think perhaps we should correct that and have this symbol, the modern symbol for a lamp, and there we go. But what I'd like actually is I'd like two lamps on with the same brightness. So here we go. there's the second one in parallel. Okie doke. And you know, you can draw relays lots of different ways, but I hope you can see how it works now. Turn on a little small circuit, okay, very small current, small voltage. Magnet pulls this metal iron armature round, pushes the contacts together and turns on a high voltage or a high current circuit. So I do hope you found that video useful and you have a better understanding of electromagnetism and electromagnetic devices. I'll probably be making another one soon, I hope, on motors, and that will sort of finish off the electromagnetism topic. So I look forward to seeing you next time.